Hello, everyone. Welcome to my presentation. The title that I'm going to present is Living Structure as the Theoretical Foundation for Teaching and Learning Cartography. This presentation is intended to advocate living structure as a scientific foundation of cartography. Living structure is a physical phenomenon and a mathematical structure. It existing pervasively in our surroundings, in buildings, in gardens, in streets, in cities, and in every part of space. As a mathematical structure, it consists of the far more small substructures than larger ones. In this presentation, I will argue and demonstrate that it is essentially the living structure or the recording notion of the far more small than largest that makes maps and mapping possible. Living structure should become the core of the cartography. I will begin with the question, what is living structure? And make it clear with two simple examples. I will present the two fundamental laws of living structure for understanding the Earth's surface as a living structure. Scaling law is characterized by the recurring notion of the far more small than largest, whereas the turbulence law is commonly referred to as the first law of geography. Herewith, I rephrase the first law of geography as the notion of the modus similar, in contrast to that of the far more small and largest. In order to see living structure, we must take the right perspective. So I will demonstrate why perspective matters. I will show that mapping is essentially a head-to-bricks processing. By mapping, I mean statistical or thematic mapping, map generalization, perception of beauty or map quality, and cognitive mapping. Finally, I will draw a conclusion by highlighting some key points of this presentation. What is living structure? It is such structure in which there are far more small substructures than larger ones. Taking the dataset of the 10 numbers, 1, a hive, 1/3, 1/4, and 1/10. For example, it is a living structure, for it consists of the far more small than largest. As shown in this diagram, the average of these 10 numbers, 0.29, partitions the 10 numbers into two parts: the head for those larger than the average, and the tail for those smaller than the average. Interestingly, this partition into the head and the tail can continue for the head again. With the second average, on the sixth one, the three numbers in the head are partitioned again into the head and the tail. Thus, the notion of the far more small than largest recurs twice, meeting the minimal condition of being a living structure. The head-to-bricks is a new classification scheme we developed for data with a heavy-tail distribution. It is a recursive function as illustrated by the dataset of the 10 numbers. Head-to-bricks has been widely used to various applications, and the method itself has also been extended from head-to-bricks 1.0 to head-to-bricks 2.0. The major difference between these two versions lies on the threshold for ending the recursive processing. For the head-to-bricks 1.0, it requires the head percentage must be less than 40% for every iteration. For the head-to-bricks 2.0, this requirement is relaxed. Instead of the every iteration, the 40% is for all the iterations on average. In other words, there is no need to require for every iteration to meet this 40% condition. Let's now further examine this painting, namely composition by the Dutch painter Pieter Mondriaan, one of the most famous 20th century artists who is well known for using simple geometric shapes and the primary colors of red, yellow, and blue. Conventionally, we see this painting consists of the seven pieces, among which the most salient pieces are in red, yellow, and blue. Instead of the static view or Lego-like assembly view, we can see this painting consisting of the 18 recursively defined substructures as shown in panels B, C, D, and E. In total, 18 substructures. In other words, the painting is evolved from an empty square in a step-by-step fashion. First, from panel B to C, there are far more newborn or newly generated substructures than older ones. From C to D, there are also far more newborns than older ones. Thus, the notion of the far more newborns than older ones recurs twice. So it is a living structure. In addition, we can notice that they are at each iteration, except the first, far more small than largest. Having seen these two examples, it is not difficult to figure out what a living structure is. It is such a structure in which they are far more small than largest. Note that the notion of the far more small than largest must be recurring across all scales for large substructures. On the other hand, small substructures are more similar in size on each of the scales. Having seen these two examples of living structure, now let's take a look at the definition of living structure or wholeness. Here is a definition by Alexander to quote, "I propose a view of physical reality which is dominated by the existence of this one particular structure W, the wholeness. In any given region of space, some subregions have high intensity as centers, others have less. Many subregions have weak intensity or none at all. The overall configuration of the nested centers, together with their relative intensity, comprise a single structure. I define this structure as the wholeness of that region." End quote. Note that the centers Alexander used here are what I refer to as substructures, which are recursively defined. I define living structure or wholeness as a structure in which there are many recursively defined substructures with an inherent hierarchy. Across the hierarchy, there are far more small substructures than larger ones. Yet on each of the hierarchy, substructures are more similar in size. These two notions, far more small than largest and more similar, underline respectively the scaling law and turbulence law. A living structure is said to be governed by these two fundamental laws. Living structure is a physical phenomenon that pervasively existing in any part of space or matter. Just an air, we cannot see it, but it is everywhere. Living structure can be defined mathematically and can be well reflected psychologically in the human mind and the heart. I formulated scaling law out of the notion or recurring notion of far more small than largest. It is a defect, spatial heterogeneity, one of the two spatial properties. They are far more small than larger one across all scales, ranging from the smallest to the largest in geographical space or the Earth's surface. The notion of the far more small than larger ones recurs multiple times rather than just once. Note that it is not more small than largest, but far more small than largest, with far indicate the disproportionality between smalls and the largest and between the numbers of the smalls and the largest. Tobin's law is also called the first law of geography, and it is about spatial homogeneity or spatial dependency. Everything is related to everything else, but the near things are more related than distant things. In other words, nearby things tend to be more similar or related. In order to see living structure, we must take the right perspective. For example, seen from the perspective of street segments or junctions, a street network is a non-living structure. However, seen from individual streets, the street network is a living structure because there are far more short streets than long ones, or far more less connected streets than the well-connected ones. As commonly conceived, a linear geographical feature such as a coastline or the highway consists of more similar sized segments, so it is a non-living structure. However, seen from the perspective of individual bands, which are recursively defined, there are far more small bands than larger ones. So a linear geographical feature is a living structure. A set of the points is commonly seen as a fragmented, non-living structure. But through building up a triangulated, irregular network and chop it into many triangles, we will find out there are far more small triangles than larger ones. Using the head-tail bricks, we will find out that all the small triangles, smaller than the average, will form what we call nature cities. To summarize, the Earth's surface is a living structure with the recurring notion of far more small and larger at different scales, ranging from the global scale, continental scale, the country scale, the city scale, to building facade scales, and even down to the ornament scale. It is essentially the living structure that makes maps and mapping possible. It is the living structure that lies at the core of cartography. It is the living structure that evokes a sense of the beauty of maps in the human mind, the heart. Living structure represents a big paradigm shift from Rene Descartes' mechanistic worldview to Alfred Whitehead's organismic worldview. The father of the fractal geometry framework, Mandelbrot, used to see that Euclidean geometric shapes are cold and dry, a term with a clear sense of the feeling on it. In contrast to the feeling of cold and dry, the term living structure conveys some positive feeling on it. The organismic worldview first conceived by the British philosopher Alfred Whitehead, who extended the mechanistic worldview to include the human beings as part of the world picture. In other words, we human beings are part of the world rather than separated from the world. Under the organismic worldview, Alexander developed a certain view of space. Space is neither lifeless nor neutral, but a living structure capable of being more living or less living. Under the organic view of space, mapping can be considered to be a head-tail bricks processing. In the following few slides, we are going to show how the different mapping activity can be viewed as a head-tail bricks processing. Here is a set of the 1,000 dots whose value follow a zip law-like distribution. It means that the largest value is twice as big as second largest, 3 times as big as third largest, and so on and so forth. Applied in head-tail bricks, we can notice that there are 4 hierarchical levels because the notion of the far more small than largest recurs 3 times. So the H index is 4. The pattern induced by the head-tail bricks looks very living, thus reflect very well the underlying living structure of the dataset. Here is 5 levels of scale of British coastline generalized through the recursively applying the head-tail bricks. It is the underlying living structure that tricks a sense of beauty of maps. Here we see how maps are perceived probably as works of art. To the left, it is a street network around the Stockholm region. Clearly, there are many less connected streets in blue and very few well-connected streets in red and yellow. To the right, we see the settlement pattern in Chicago region, and there are far more small settlements than larger ones. We have recently developed the notion of the structure beauty for characterizing liveliness or degree of beauty of city plan. To the left of the screen, it is the city plan for the city of London, and the 6 colored panels show its 6 hierarchical levels. From them, we can see how it was transformed to become more and more living. To the right of the screen, it is part of the Manhattan city plan, and the 3 colored panels show its 3 hierarchical levels. In comparison of these 2 city plans, there is little doubt that the city of London is more living or more structurally beautiful. Not only cartographic mapping, but also cognitive mapping is essentially governed by the head-tail bricks process. Given the underlying living structure, a map can be abstracted as the head of the head of the head, and so on. Those in the top head are landmarks that form the cognitive map, while those in different heads constitute the different scale maps of different scale. If we show all the nature cities in the UK, it will look like a hairpin. By removing those in the tail recursively, the underlying living structure will be appearing. In other words, the head reflects the whole, or the head is self-similar to the whole. Okay, it is time to draw a conclusion of this presentation. Here is a few points to highlight. Living structure is a physical phenomenon and a mathematical structure that consists of the far more small substructures than larger ones. Living structure represents a paradigm shift from Euclidean and Cartesian geometry to fractal and living geometry, from Gaussian statistics to correlation statistics, and from Cartesian mechanistic worldview to wide-heading organismic worldview. Scaling law or living structure is universal, pervasively existing in our surroundings. Mapping is essentially a head-tail bricks processing applied to various mapping activities. A map is the map of the map of the map, and so on, just as a living data set is the head of the head of the head, and so on. To learn more about the living structure and how it can be used to guide maps and mapping, I recommend these videos. Thank you very much for your attention. I have enjoyed the presentation. Any questions and comments are very welcome.